Number 9 actually starts with number 8, about corn yield. And just to remind you, sometimes they don't give you the summary statistic. You are just given data. That's not a problem, right? I just entered that into my calculator, made sure I double-checked the data, and then this is stat calc. Enter all that. And we get ourselves a sample mean. And by the way, there is a sample standard deviation here with S. And I made a note of that as 12.3. But they do tell us in the problem a population sigma, which is a little bit lower. Usually population sigma is lower than your sample standard deviation. And then they ask you to do 3 different confidence intervals. And then what happens to your margin of error as the confidence increases. Okay, so I did this in 3 different colors. First of all, the statistics over here are the same for all 3 intervals. So let's just see the sample size doesn't change. The sample mean that came from our calculator doesn't change. I did write this down as the sample standard deviation, but we're not actually using that if we have the population standard deviation. That's a little note, though, to our future selves, that in the next chapter we'll be using t-values and we won't know sigma. Since we know sigma, we just take that and divide it by square root of n, and we get the standard deviation of the sample mean, which is not 10 but 2.58, and then we use these numbers to calculate all of these. For 90%, we get that z-score. That's from table C. You multiply z times this sigma 2.58 and you get a margin of error. And here we can see the difference in margin of error from 90 to 95 to 99. So what's happening? The margin of error is increasing, because as we take more and more probability and look at the tails of our normal curve, we're going further out to a wider margin. So to be more sure, we're going to open up our confidence interval a little bit. And so we get, at a 90%, we have a kind of a nice narrow range here from 119.6 to 128.0. That's actually less than 10, right? But then here it is a little more than 10, and here it's about 13.2. So the intervals are increasing with confidence level. So sometimes we want to kind of zero in. We'd rather have plus or minus 3% than plus or minus 10%. So we go with the 90% confidence level. However, in life and death situations where, improperly inferring something about the mean might cause your plane to crash or someone to have a heart attack, we tend to go with the 99% confidence level, even though that seems to be less accurate, so to speak, or just less zeroed in on. Okay, well, let's take a look at that in pictures. I took the colors down here. You didn't have to do this. So this is, an example problem that I really should have given you before you tried number 9. But here it is. You can see that the green interval is not as wide, right? So, and we kind of like that. Like I said, I'd rather tell you I've figured out it's 55% plus or minus 2%. Instead of 55% plus or minus 20%. That's not, really telling us much. But there is the center. The sample mean is the center, and then our different confidence intervals. Okay, number 9 was the real question that you were supposed to have worked on. And how do these compare? What happens when you basically quadruple the sample size, take it from 15 to 60? Well, interestingly enough, when that goes up by 4 and then you take the square root, we're dividing this by 2 more. So our 2.58 got cut exactly in half, divided by 2, because we're just dividing by another square root of 4 here. So that's an interesting relationship. You quadruple the size of the sample and you cut the standard deviation in half. And since we have a smaller standard deviation to multiply, it's still 1.96, but this margin of error is going to be half as big as it was. What was it up here? It was 5.06. Cut that in half, that'd be 2.5 plus another little 3/100ths. And there you are, 2.5 plus your another 3/100ths there. The confidence interval is much narrower. It's basically 5 units wide. And I did a horrible job of sketching the curve here, so if you'll forgive the artwork here. But I did try to draw these in line to show you that, sure, changing the confidence level can change the width of your interval, but changing your sample size will also, by changing the shape of the curve, change your interval. We still have 95%, so 2.5% tails, 2.5% here, 2.5% here. However, the shape is different. It's pointier, it's narrower because we have a smaller standard deviation. Number 12 asks us about some tiny numbers. A scale that's supposed to read exactly 10 grams has a little bit of error, and so we're wondering what that average error might be. It's weighed 5 times. I don't know why the sample size is so small, but we're okay because it's a normally distributed population of errors. And we're given some information. So part of the trick to these problems is pulling out the right numbers. We've got a sample size, we've got a sample mean, and a standard deviation that's been given to us. Just right away you can take the sigma and the n and calculate yourself a sampling standard deviation, which is very tiny. And then they ask us for something a little bit unusual, a 98% confidence level. Well, when you go to the table, you see what is the magic critical value. That's not one of the ones we usually memorize, but it is 2.326 on our table. Sometimes with 3 digits, that's just 233. So above 196, but below the 2.576 for the 99%. And if you multiply this critical value times this little standard deviation, you get a margin of error of 0.00021. Plus and minus that, and you get a confidence interval. And probably one of the reasons we did this is to see, is it always going to be above these scales? Are they biased to overestimate 10 grams? And sure enough, we have a 98% chance that true mean error is between 0.0021 and 0.0025. In other words, definitely above 10. Part B asks you about sample size. What if we wanted to get, what if we want the margin of error to not be this, but cut that down basically in half to a 10,000th of a gram? Well, we have this formula, and we can just do a little bit of algebra to solve for n. What are we going to do? We're going to square everything, square both sides, and then we'll get n there. And if we multiply n over and divide e squared over, we get n. The square root of n has been squared, so we just got n, which is the whole point of squaring it. And then we have the z star squared times sigma squared, also known as the variance, divided by the margin of error that we want squared. So we know all these numbers, and I'll stop the camera and plug these in, but we know the critical value, we know the population standard deviation, and we know the error that we want. So I've plugged in the critical value, the sigma, and the margin of error. And this all comes out to, believe it or not, 21.6. And we're talking about the number of times. This is a discrete number, so we need to round this up to 22. But our sample size of 22 then would give us this desired margin of error.